Welcome to UGC lecture series Linear Integrated Circuits. In this lecture, we are going to see about the AC characteristics, the linear applications of operational amplifier. The previous lecture, we have seen two characteristics of AC, and which is the frequency response and stability. The last one is the slew rate, and in this lecture we are going to discuss about it. What are the linear applications of operational amplifier? There are many linear applications, out of which we are discussing about the summing amplifier, adder, differential amplifier and subtractor. What is a slew rate? It is defined as the maximum rate of change of output voltage caused by a step input voltage, and which is specified in volts per microseconds. For example, if it is specified as 1 volt per microseconds, which shows that the output rises or falls by 1 volt in 1 microsecond. The ideal slew rate is infinite. And what is the reason for the slew rate? Actually, this is because of a capacitor at the output. It may be either a internal capacitor or it is the external capacitor for frequency compensation. So, this capacitor which prevents the output to respond immediate or instantaneously to the change in the input voltage. So, the rate at which the voltage across the capacitor increases is given by dVc by dt is equal to, this is I by C, the current flowing through the capacitor divided by the value of the capacitor. So, this is the equation which gives you that the condition of the slew rate. The slew rate must be actually greater than or equal to 2 pi f Vm. Here, if this condition is satisfied, then the output will not have any distortions. So, the slew rate will be specified by the manufacturer, and if the specified slew rate is greater than the input frequency what we are applying and the peak voltage Vm what we are setting for the input signal. So, f is the operating frequency and Vm is the peak amplitude of the waveform. So, consider this waveform at the output of the operational amplifier, and this is the calculation of the slew rate for that particular waveform, which is 10 volts, that is volts per microseconds is the slew rate. So, the rate of change of the output voltage, the maximum rate of change of the output voltage for the input step input signal, that is the explanation for the slew rate. So, the maximum rate of change of the output voltage is 10 volts for this second for 0.667 microseconds. If you calculate, it is 15 volt per microseconds. So, which is telling that for in 1 microsecond 15 volts is increasing or decreasing in this case. So, the next is the linear applications of linear applications of the operational amplifier. So, in the first lecture we have seen the inverting amplifier, non-inverting amplifier and the voltage follower. These are some of the applications of linear applications of the operational amplifier. So, here we are going to discuss about the inverting summer. We know that in an inverting amplifier which gives you 180 degree phase shift between the input and output. So, whenever we are dealing with the inverting amplifier or a inverting summer, then we will be having a definitely 180 degree phase shift between the input and output. So, in this case the input signal is given to the negative terminal, and there are two input signals is given through R1 and R2. So, V1 and V2 are the input signals which are going to summed up at the output, and if it is a summing amplifier, then we have to design in such a way that the resistance RF and the input resistors R1 and R2 is going to amplify the sum of the input signals in this case. We are going to find out what is the output for this particular circuit, and this is the inverting summer. So, this must be equal to V1 plus V2, that has to be the output of this summer. So, here R1 is the resistance given for the input signal V1 and R2 for V2, the feedback resistor is RF. So, consider the current flowing through this R1 as I1 and the current flowing through R2 as I2, and consider this as node A, and the current flowing through RF is IF. So, consider this as node A, this point as node A, the current flowing through R1 as I1 and current flowing through this R2 I2 and through RF it is IF. So, if you write an equation for this node A, KCL for this node A, KCL at A, which gives you I1 plus I2 plus IF is equal to 0. This KCL tells that the sum of the current flowing towards the node is equal to the sum of the current flowing away from the node. So, in this circuit, these currents are flowing towards the node A and only one current which is flowing away from node A, that is IB minus. IB minus is the bias current which is flowing away from node A and which is assumed to be equal to 0 since the input impedance is infinity. So, what is I1? It is V1 by R1 and I2 is V2 by R2, V out by RF is equal to 0, that is the output voltage V0 by RF is equal to 0. So, we have to calculate V0. So, V0 by RF is taken in the left hand side minus V1 by R1 minus V2 by R2 and V0 is equal to take minus out here and bring this RF in this side. So, you will be having V1 plus V2 and if the resistors all are equal, R1 is equal to R2 is equal to RF, then these two resistors will be considered as RF and these two will be getting cancelled. So, finally, it is V1 plus V2. Since you have applied the input signals to the negative terminal, then the minus shows that 180 degree phase shift between the input and the output. So, it is the sum of the voltages given at the input terminal, negative terminal V1 and V2, that is the output of the inverting summer. But we have to keep all the resistors are equal. This is the non-inverting summer. So, what is the difference between the previous circuit and the present circuit? Here also the input signal V1 and V2 is given through two resistors R1 and R2, but not to the negative terminal, it is given to the positive terminal. That is why it is non-inverting summer. And here the feedback is always given to the negative terminal through the resistance RA RB and output is taken at the output terminal VO. So, consider again this consider this point as node A and apply the KCL at node A. In the same way, we have to calculate the output of the non-inverting summer also. KCL at node A. So, I1 is the current flowing, I1 is the current flowing through R1 and I2 is R2, and here there is no circuit and only the current IB plus is flowing towards the positive terminal, but IB plus is considered as 0 since the input impedance is infinity. So, there is only one current flowing through these, there is two currents I1 and I2, and at this node A, the node A will have a voltage which is equal to this voltage, and consider that voltage as VA. Since these two terminals are virtually equal, then we have to consider this voltage as VA. Whatever the voltage across the resistance RB will be considered here as VA. So, I1 is V1 minus VA by R1, I2 is V2 minus VA by R2 equal to 0. That is the KCL. I1 plus I2 is equal to 0, since IB plus is 0. So, I1, which is in the circuit, it is given as IR1 and IR2. Now, for simplification, I have taken it as I1 and I2. I1 is given as V1 minus VA by R1 plus I2 is given as V2 minus VA by R2, and that is equal to 0. So, take the voltage VA as common. So, V1 by R1 plus V2 by R2 minus VA by R1 minus VA by R2 is equal to 0. V1 by R1 plus V2 by R2 is equal to VA by R1 plus VA by R2. So, we have to see if the values of the resistors, so that the voltage, the output voltage will be equal to V1 plus V2. So, actually from this equation we are obtaining only VA. VA is V1 by R1 plus V2 by R2 divided by 1 by R1 plus 1 by R2. So, this is VA, and the output voltage in this case is actually the gain of the amplifier 1 plus the resistance, feedback resistance divided by the input resistance R1 into VA. If you see the feedback resistance, I have taken it as RF, and the input resistance, which is RB, I will take this as R. Do not consider this R1, since we have taken R1 earlier. So, this is the output of a non-inverting summer. So, in this case you have to substitute what is the value of VA. If you substitute the value of VA, you will have 1 plus RF by R into this voltage V1 by R1 plus V2 by R2 divided by 1 by R1 plus 1 by R2. So, now you have to choose the values of the resistance in such a way that the output will be equal to V0 is equal to V1 plus V2. So, what must be the value you have to give? So, you consider if these resistors are equal, you will be having a value 2 here for this product, and if all the resistors are equal, R1 is equal to R2, then this will be V1 plus V2 by R1. If you take it, R2 is equal to R1. Again here it will be 2 by R1. So, consider all the values of the resistors are equal. R is equal to RF is equal to R1 is equal to R2. So, for this value the output will be, if you substitute RF is equal to R1, then this term will have 1. So, the product will be 2, and here V1 by R1 plus V2 by R1. So, V1 plus V2 by R1, here it is 2 by R1. So, if you consider these two R1 and R2 as equal, this R1 will get cancelled, this 2 will get cancelled. Finally, you will be having V0 is equal to V1 plus V2. So, this is the output of the non-inverting summer. So, in this case there is no negative sign at the output. So, there is no phase shift between the input and output. This circuit will give you only the summation of the two input voltages given to the positive terminal of operational amplifier. If it is going to be a non-inverting summing amplifier, then we have to choose the values of the resistance accordingly to amplify the summation of the input signals V1 plus V2. If all are equal, then it is going to only produce the sum of the two input signals. And the next circuit is the differential amplifier circuit. From the name itself, it is clear that the circuit is going to amplify the difference between the two input signals V1 and V2. It is going to amplify the minute difference between the two input signals V1 and V2. That is the use of the differential amplifier. So, the minute the V1 and V2, if it has a difference in millivolts range, then the differential amplifier will amplify the range of the millivolt into 100 times, and it produces the output in volts. So, what are the two input signals given? V1 to the negative terminal, V2 to the positive terminal, and feedback is through R3. So, how will you calculate the output of the differential amplifier circuit? Since we have two input signals at the two input terminals plus and minus, we can use the superposition theorem to calculate the output. In superposition theorem, we have to set one of the input signals as 0 and find out the output for the remaining input signal. For example, if V2 is kept 0, then the output for V1 alone can be calculated first, and for the second case, keep V1 as 0 and output for V2 alone can be calculated, and finally add both the outputs to produce the output of the entire circuit if both the input signals are present. Okay. So, now we have to remind this input resistors R1, R2, R1, R2, the feedback resistor is R3, and this positive or compensation is R4. Okay. Now, using the superposition theorem, the output voltage is going to be derived. Using superposition theorem, we can derive the output of the differential amplifier. For case 1, V2 is kept 0, only V1 is given for the circuit. So, at that time, VO is taken as VO1. So, now from the circuit, if you see, V2 is 0 and V1 is given to the negative terminal. So, this amplifier will now work as a inverting amplifier. It is an inverting amplifier. So, what is the inverting amplifier's output? The gain is actually minus R3 by R1. So, VO1 can be equated to minus R3 by R1 into V1. V1 is only given. So, this is VO1, and if for the next case, if V1 is 0 and V2 is given, then the output is taken as V02, and now it is non-inverting amplifier. When you see the circuit, if V2 alone is produced, if V2 alone is applied to the positive terminal, this is grounded, then there is no signal to the negative terminal, only for the positive terminal we are giving the signal, then this amplifier is acting as a non-inverting amplifier. And what is the gain of the non-inverting amplifier for this circuit? It is 1 plus Rf by R in. Rf is R3 here and Rn is R1. So, V02 can be given as 1 plus R3 by R1 into VA. What is VA? In this circuit, you have to calculate VA, and this voltage will be amplified by the factor of 1 plus R3 by R1. So, how will you calculate VA? VA is equal to the resistance R4 across which the voltage is VA. So, R4 into V2 divided by R2 plus R4. This is the potential divider rule. So, here there are two potential dividers, that is the resistors R2, R4. So, across R4 the voltage is represented as VA, which is going to be the input of the amplifier. So, to find out the voltage across the R4, we have to apply a potential divider rule, that is the input voltage is V2 multiplied with the resistance R4 divided by the total potential dividers, that is R4 V2 by R2 plus R4. So, substitute VA here, it is 1 plus R3 by R1, VA is R4 V2 by R2 plus R4. This is your V0, VO2. Finally, if the two input voltages are given, we have to take both the case. So, the output voltage will be the sum of the two output voltages when V2 is equal to 0 and V1 is equal to 0. So, now add both the both the output voltages, it is minus R3 by R1 into V1 plus 1 plus R3 by R1. So, this is the gain of the non-inverting amplifier into the input voltage, it is R4 V2 by R2 plus R4. So, now we have to assume the values of these resistors so that the differential amplifier is going to produce the amplified version of the difference between the two input signals. Now, if the resistors R1 is equal to R2 and the feedback resistor R3 is equal to the R compensation resistor R4, what is the effect produced at the output of the differential amplifier? Keep this R3 minus R3 by R1 as such, V1 plus, so if this 1 plus R3 by R1 here, R1, so if you take LCM, then it will be R1 plus R3 by R1 and R2 plus R4, these two terms will be getting cancelled. So, if you take LCM, it is R1 plus R3 by R1. So, if by this assumption R1 is equated to R2 and R3 is equated to R4. So, this term will be cancelled, and also this R1 and R4 can be taken as R4 as R3 and R1 as R1 into V2. This is the output now. So, now take R3 by R1 out, the voltages remaining is V2 minus V1. So, this is the output of the differential amplifier circuit, and which is amplified version of the difference between the two input signals V2 and V1. So, here V2 is given to the positive terminal and V1 is given to the negative terminal, then the output is derived as R3 by R1 into V2 minus V1. So, this V2 is the positive terminal and minus stands for the voltage V1. So, this R3 and R1 is going to decide the amplification factor of this particular differential amplifier circuit. Assume always the resistance R1 as high, so say 10 kilo ohms, and R3 can be designed according to the specification. So, here this, if the difference between these two signals are in the range of millivolts, even this millivolts range of the difference can be amplified by the factor of R3 by R1, and it can be produced in the range of volts, and that is the main advantage of the differential amplifier circuit. This is the another example of a linear application of operational amplifier. And this differential amplifier, if you assume again these two resistors are equal, then it is going to be a subtractor V2 minus V1. If R3 and R1 are equal, then it is the output voltage is just the difference between the two input signals V2 and V1. That is given here. The subtractor, which is basically a differential amplifier, if it is not going to amplify, it is only giving the subtraction results of the two input signals, then it is the subtractor. and for that we have to assume these two input resistances are equal and all the resistances are equal. If all the resistances are equal, then this circuit is a subtractor. And as of now we have seen an inverting summer, non-inverting summer, and the differential amplifier circuit, and finally subtractor also we have seen. And in the linear application, one more application is there. It is a adder and subtractor. It is possible to perform the addition and subtraction simultaneously with a single operational amplifier using the given circuit. It is again the by superposition theorem we can get the output. Okay, this consider this circuit. Which has the two input terminals, and to the two input terminal we are applying two input voltages. Say this is V1, this is V2, all the resistors are considered as equal. So, it is represented as R. So, this is also R, every resistor is equal, and another input voltages are given V3 and V4. Feedback resistor is also equal to the input resistor and the compensation resistor, and so it is R. So, this is the circuit for adder and subtractor. We have given V1, V2 to the inverting amplifier, V3, V4 to the non-inverting amplifier. So, what may be the result of this particular circuit? It is actually the summation of V3 and V4 minus the summation of V1 and V2. This has to be the result of the adder and subtractor circuit in a single operational amplifier. Using superposition theorem, you have to obtain the output. Say for example, the output VO1 is the output voltage when only V1 is given, and VO2 only when V2 is given, and VO3 only when V3 is given, VO4 only when V4 is given. Okay, if only V1 is given, all the input voltages are equal to 0. So, VO1 is the output only when V1 is given. In that case, all the voltages are equal to 0. If V1 alone is given, then you have to consider this is a inverting amplifier. So, for inverting amplifier, we know that the gain is minus RF by R1. Here all the resistors are equal. So, it is R by R into the input voltage V1. So, finally, it is minus V1. Similarly, for V02, only V2 is given, all other input voltages are equal to 0. So, again it is a inverting amplifier only with V2 with the resistor R and R. So, minus R by R into V2. So, the final value is minus V2. All others are equal to 0. V3 is given to the positive terminal, so it is a non-inverting amplifier. For a non-inverting amplifier, the gain is 1 plus RF by R1. All the resistors are equal, so it is 1 plus R by R, and the input voltage V3, input voltage is V3, so it is 1 plus R by R into V3. So, here it is 2 V3, and V4 is 1 plus R by R. In this case, you have to calculate this voltage VA, and actually this is VA. Calculate VA in this case. For V3 is given, VA is by using potential divider rule, R into V3 by 2R, R plus R. So, it is V3 by 2, and if you substitute here 2 V3 by 2, it is only V3. Similarly, for V4 alone is given, it is only V4 will be obtained. And finally, the output voltage will be equal to the input voltage, will be equal to this V3 plus V4 minus V1 plus V2 if you add all the voltages. The output voltage is given as V01 plus V02 plus V03 plus V04. When you add all the voltages, then you will be getting this output voltage. So this is the example of an adder and subtractor with the only V1, V2, V3, V4. You can connect other signals across this V1 and V2, again this V3 and V4. So in this session we have discussed about the adder, subtractor and differential amplifier, and one more circuit in a single operational amplifier, adder and subtractor has been implemented. Thank you.